Hello, my name is Craig Topper. I work on the RISC-V backend for Sci-Fi. Today I'm going to talk about scalar sign extend optimizations we've implemented in LLVM for RISC-V. To begin, I'm going to give a basic introduction to RISC-V, then I'll go over SelectionDAG optimizations we've done, and finally we'll talk about a couple just custom optimization passes we've created. So for those of you who don't know, RISC-V has two main variants, RV32i and RV64i, where the 32 or 64 refers to the size of the scalar integer registers. Unlike targets like x86, 64, or AR64, there are no 32-bit subregisters for RV64i. There's just one size of register. All of the computational instructions are defined to read and write this whole register. Both RV32i and RV64i can load and store 1, 2, or 4 bytes, and RV64i can also load and store 8 bytes. If the loaded value is smaller than the register size, we have instructions to both sign or zero extend to the register size. Because there's only one size of registers, operations involving narrower types often require additional instructions. On the left, I have a C++ program that adds two 16-bit signed integers and computes the 16-bit result of comparing to a constant. So there. On the right, I have the generated assembly for this function. The highlighted lines show two shift instructions that we need to use to sign extend the result, to sign extend the lower 16 bits of the add result to the full register size so that we can use the comparison that reads the whole register. Since RISC-V was designed for simplicity, there are no dedicated instructions for doing this sign extend, so we have to do this two instructions shift sequence. And the only difference between the two sequences is the number, how many bits you need to shift to get this bit 15 to the MSB of the register. So the rest of the talk is primarily going to focus on the 64-bit variant of RISC-V. As you probably know, C and C++ code often contains many 32-bit integers. The int type on RISC-V is 32 bits, as you'd expect, and C integer promotion rules require that operations on short and char types get promoted to int or unsigned int. Since the creators of RV64i recognized that these extra shift instructions would hurt the performance of this kind of code, they added some extra instructions specific to the 64-bit variant to avoid the unnecessary instructions that I showed before. So most of the binary arithmetic instructions have an additional version that only uses the lower 32 bits of their input and then sign extends their result by copying bit 31 to the upper 32 bits. These instructions have a W at the end of their name to distinguish them, where W stands for word. RISC-V's word size is 32, even for 64 bits. The exceptions to this are that AND, OR, and XOR instructions do not have W versions. For those instructions, if you pass the sign extended value, if both inputs are sign extended, the result of them would still be sign extended. So they don't need the W instruction if you use them well everywhere else. So by using the W instructions to sign extend values, we can often avoid any extra instructions to perform a signed comparison of 32-bit values. And it also works out that you can do an unsigned comparison using sign extended values as well. And so since the ISA has made it cheaper to sign extend a value when it's produced, the ABI was made to require both int and unsigned int to always be passed in sign extended form. And at worst, if we do need to do a sign extend, we can sign extend a 32-bit value by doing an add with immediate W instruction using a zero immediate. We have a special alias to this that we call sext.w or sign extend W. Unfortunately, we still require two shift instructions to do a zero extend to 32 bits. So we want to avoid those if possible. So if we go back to our earlier example, I've replaced the int32 type replaced the 16-bit types with 32-bit integers, and now we don't need any extra shift instructions because we have used the W instruction here, which will do the add and then immediately sign extend the result before it's written to the register. So that's the kind of optimizations we get to do using these instructions to avoid the extra comparison. So now that I've gone over the basics of RISC-V, I'm going to move on to how we create W instructions in SelectionDAG. So all of the operations on i32 types will need to be promoted to 64-bit to an i64 type, as we only have the one register class marked as legal in SelectionDAG. Promotion is defined in SelectionDAG to allow you to put any value in the upper bits of the register. We choose to use sign extensions so that we can make use of these W instructions and hopefully avoid extra instructions later. So like every other target, we use truncating stores to represent storing part of a register, or extending loads to represent loading a small value and extending it to fill the register. Some operations would normally require sign extend or zero and extend operations to be inserted to safely promote their inputs. This is what we saw with the compare earlier. So SelectionDAG represents sign extension by an operation called sign extend in reg, which we later turn into a sign extend W. And the zero extend for most of SelectionDAG is an AND with 32 ones. And we have to convert this to a shift left and a shift right at instruction selection time. The sign extend and zero extend is required problem not only affects compares, but also affects right shifts, division, remainder, and right shifts, division, and remainder. But we can avoid this if we use the W versions of those, since it would ignore the upper bits of the input. And we also need to zero extend the shift amount of all shifts to make sure the value stays between 0 and 31. Otherwise, it becomes undefined behavior. So ideally, we'd insert these sign extend in reg and AND operations before any of the instructions that require it, and then at instruction selection time at the end of SelectionDAG, we would pattern match those to W instructions. Unfortunately, if you work out how the patterns work, they don't always guarantee to produce a sign extended result, so they don't map naturally to a W instruction. But as I said before, we're allowed to do anything with the upper bits, so we were free to use a sign extend. So once the operation has been promoted, we can't tell if it had been promoted or it was written that way in the original source code. So it's hard to determine that we could have used the W instruction. So we've done a few things for different operations to take advantage of this, or to pick W instructions well. So for all of for the division and remainder instructions, we use custom opcodes in RISC-V that are defined to sign extend the results, so we can keep track of this information. And then comparisons, we always promote using a sign extend in reg for both signed and unsigned compares. And we insert a sign extend in reg after the add, sub, mul, and shift left by constant operations. That way, all of the uses we'll see the sign extended result, so we can pattern match those to add W and sub W, etc. later. The DAG combine optimizations can often optimize out some of the redundant sign extend in regs this will create. Unfortunately, the DAG combine can also remove some unneeded sign extend in reg if the sign extended part is not used by later operations. Sometimes this occurs for only a subset of the use, which creates a problem that we were trying to avoid by aggressively omitting the sign extends in the first place. So in this example, before DAG combine optimizations, after we legalize, we have an add and a sign extend in reg that is used by both a return and a truncating store. The return needs to be sign extended because of the ABI, but the truncating store is only going to store 32 bits. So the truncating store doesn't need this value to be sign extended. So DAG combine helpfully puts the sign extend in reg and the truncating store in parallel, both using the add, because it thinks this is going to have a non-zero cost. This results in the generated assembly over here, where we have an extra sign extend W instruction because we weren't able to use an add W for both uses. So the ideal assembly would have just used an add W that goes to both the store word and the return. So to improve the generated code, we try to undo this DAG combine optimization at the end of SelectionDAG during instruction selection. When instruction selection is done by starting at the end of the basic block and working backwards. So by the time we reach the add operation in this graph over here, we've already selected all of its users. And so we do a quick check by just looping over all the users, and if they're all an instruction that is known to ignore the upper bits, we can go ahead and select the add as add W instead of add. And then once we've selected the entire graph, we will go back through and look at all of the sign extend Ws, and if their input is an add W, we will just delete the sign extend W and replace the uses with the add W. This sort of reverses the SelectionDAG optimization. There are still some improvements that can be made here. The current code only looks at the direct users of the add, so we miss some cases where the upper bits are unused, but we would need to look through other instructions and check their uses too. A perfect example of this is the add or and XOR instructions. They only demand the bits, they only demand the same bits as are demanded of them. So we could recursively look through the add or and XOR instructions to improve this. It's worth reconsidering if we can just stop DAG combined from doing this optimization on RISC-V rather than trying to undo it later. Okay, so now I'm going to go over a couple of the RISC-V optimization passes that we've added. The first pass removes redundant sign extend W instructions that are left behind after SelectionDAG. In many cases, SelectionDAG can share information about the number of sign bits or number of redundant sign bits a value has between basic blocks. This information can then be used to avoid creating sign extend W instructions in a block. But because this information is saved as part of SelectionDAG visiting each block, the information is not available if the live in depends on a loop back edge, because SelectionDAG would need to revisit the loop body in order to make use of the information. So here's an example containing a redundant sign extend W after a loop and after SelectionDAG. On the left, I have a prototype for a function that takes an int by value. The ABI requires that this argument be sign extended to 64-bit, and the function foo calls this in a loop. The loop passes a variable x to bar, and this variable either comes from an add operation before it or a shift operation on the previous iteration of the loop. On the right, we can see that SelectionDAG correctly chose an add W for the add here, and an SRAIW for the shift here, but we still emitted a sign extend W for the call itself. But the inputs of the call come from this fee, and the fee uses either the add or the SRAIW, so no matter what value the fee receives, the result of the fee will be sign extended, so we didn't need this instruction. So the solution I implemented was to add a SSA machine IR pass that does a depth first search from the instruction that defines the sign extend W input, in this case the fee node. If that search encounters a W instruction, then we know the register is already sign extended. If we find an instruction that propagates sign extension, like AND, copy, or fee, we add their inputs to the search and continue. If we find any other instruction that we can't analyze, we'll keep the sign extend W, if we can't analyze, we'll terminate the search and keep the sign extend W. If the search completes without terminating early, then we know the sign extend W is unneeded and we can remove it. So this allows us to remove the loop, the instruction that SelectionDAG left behind there. So in this case, in that example, we would visit the fee, know that it propagates sign extend, so then we would add both the add W and the SRIW to the work list. And then when we visit each of them, they're considered W instructions, so they will successfully pass the search, and then we're done, and we can remove the sign extend W. We've also implemented a few special cases for the main algorithm. We record which virtual registers are mapped to sign extended arguments, and we use that information as a special case for copy instructions. We don't yet do the same for registers that are returned from calls, so we don't treat return values well yet. And then some instructions, like add, can be freely converted to a W instruction if their upper bits aren't used. We can just change what value they have. So if we encounter one of those instructions, we'll do a forward depth first search similar to the backwards one I showed before. And if that search successfully finds that all of the consuming instructions going forward don't look at the upper bits, we will mark this, and then if that is the only thing stopping us from moving a sign extend W, we will do that conversion to allow us to remove the sign extend W. And then the last pass I'm going to talk about is RISC-V CodeGen Prepare. So the middle end optimizations pretty aggressively replace sign extend instructions with zero extend if the sign bit of the input to the sign extend can be proven to be 0. But for RISC-V, zero extending an I32 to I64 is never cheaper than sign extending. It potentially requires the two shift instructions we talked about earlier. So on the left, I have a loop with a signed int induction variable that is used as an array index. So we have I and I is used there. Middle end optimizations widen this induction variable and the trip count to both be I64. Since the loop is never entered if the trip count is negative, a zero extend ends up getting used to widen it instead of a sign extend. So we have both a sign comparison here and a zero extend of the same value here. This causes an extra pair of shifts to be generated. So this ends up causing an extra pair of shifts to be generated in the loop pre-header here to do the zero extend. we already know, in order to do this compare, A1 would have already been sign extended, so it would have been free to just use a sign extend here because it would have happened in the predecessor instead of here. So we could have saved those two instructions. Now, I've currently implemented a partial solution for this that adds a pre-SelectionDAG IR pass that goes through every zero extend instruction in a basic block, and basic blocks with a single predecessor. And it checks the terminating condition of that predecessor and sees if that terminating condition implies that the sign bit is 0. And if it is, we will replace this zero extend back with a sign extend, recovering what was lost in the middle end. Okay. So, unfortunately, looking at a single predecessor is a very cheap dominator check, and it's definitely going to miss some cases. And handling more cases requires us to redo more of the optimizations, redo more of the analysis the middle end did to remove it in the first place. So I would like to figure out how we can recover this information from the middle end. So in conclusion, RISC-V is different than other well-known 64-bit architectures in that it doesn't have free zero extend. We've made a lot of progress for W instructions to avoid extra instructions, but there's still more that could be done. And I look forward to working with the community to retain knowledge from the middle end so that we can improve our ability to use sign extends instead of zero extends in the back end. I'd like to thank Alex, Luis, and Philip for their reviews and advice on these optimizations. And also thanks to Mohammed for his improvements to the sign extend W removal pass. That's it.
We can take questions now. Thanks, Rick, for the amazing talk. There are 2 mics. You can queue behind them, or I can bring this mic to you.
No questions.
So, Craig, I'm just curious, what do you see as the biggest gaps we have left? Where are the things we need to be thinking about going forward around this problem?
So some recent things I looked at, I think the not doing recursive in the SelectionDAG recovery is hurting us in some cases. I've seen one function that had over 100 sign extends left in it. I have some patches up to remove the sign extend W, improve the sign extend W removals analysis to look at on its forward search to handle store W correctly amongst other instructions. I think we still have a lot of opportunities left on the IR side. The middle end, as I said, creates a lot of zero extends, and I think that probably affects more than just that simple case I showed. And if that directly answered, I think I just gave it.
When this work is all done, how much size reductions or performance gains do you expect to have?
I don't have exact numbers handy. I do know that on one benchmark in Spec 2006, the sign extend W removed like 800 instructions from the whole program. Just happened to look at that statistic recently.
Okay. What is the base for comparison?
Well, that's how many it removed that were left behind by SelectionDAG anyway.
Okay.
Hi, thank you for the nice, well put together talk. Just a quick question. Do you think some of these cases where you had to traverse the value from different basic blocks will go away with global ISL? Or is that not the case?
I think that is I definitely think that is a possibility. I'm not sure if global ISO can handle the loop case. Maybe, is anyone familiar with global ISO that would know if we'd be able to do compute num sign bits around a loop in global ISO?
In principle, it should be, but I think there's currently like a block check because I think somebody didn't want to bother seeing if it actually worked.
Okay.
Another comment for global ISL, like this, DAG is doing this thing we don't want, and now we have to struggle to like undo it. It's sort of another benefit for global ISO because basically all your optimizations are opt-in.
Okay.
You don't have to start from this, I need to undo whatever I decide to do on its own.
Thanks.
Okay then. Thanks, Craig, for the talk. Our next talk will start at 5:35.